Gravity, an invisible sculptor, is the primary artist behind the majestic architecture of our cosmos. From the gentle sway of an apple falling to the intricate dance of galaxies, this fundamental force dictates every celestial motion and the very existence of planets. It's the silent, enduring pull that shapes worlds, influencing everything from their initial formation to their internal structure and atmospheric composition. At its core, gravity is simply the attraction between any two objects with mass. The more massive an object, the stronger its gravitational field. This elegantly simple principle, famously articulated by Isaac Newton, explains why the moon orbits Earth and why we remain firmly grounded rather than floating off into space. It's a universal handshake between everything that exists. Gravity's influence extends far beyond our everyday experience, spanning colossal cosmic distances. It's the grand orchestrator that binds billions of stars into galaxies and clusters of galaxies into superclusters. Without its persistent pull, the vast structures we observe in the universe would simply disperse, leaving an undifferentiated void. While gravity is the weakest of nature's four fundamental forces, its long-range influence makes it the dominant force on astronomical scales. Electromagnetism, for instance, is far stronger, but its effects are often cancelled out by opposing charges, whereas gravity always attracts. This cumulative effect allows it to build and maintain the largest structures in the universe. This persistent, attractive force is what compels objects into graceful, predictable orbits. Whether it's a comet swinging around the sun or a satellite circling Earth, gravity provides the continuous centripetal force necessary to keep bodies locked in their celestial dance, preventing them from flying off into the emptiness of space. Gravity also plays the role of a cosmic sculptor, shaping not just orbits, but the very forms of stellar and planetary bodies. Large enough accumulations of gas and dust under gravity's relentless compression will eventually self-gravitate into spheres, making planets and stars naturally spherical, the most energy-efficient three-dimensional shape. Understanding gravity's fundamental nature has been a cornerstone of scientific discovery, evolving from Newton's classical mechanics to Einstein's general theory of relativity, where gravity is described as the curvature of spacetime itself. This revolutionary insight helps us understand extreme gravitational environments, like black holes and the expansion of the universe. Despite its profound influence, gravity remains an elusive force. We cannot see it, hear it, or touch it directly. We only perceive its effects, the weight we feel, the tides in our oceans, the steady pull that governs the rhythm of the cosmos. Its invisible nature adds to its enduring mystery and scientific fascination. From the structure of galaxies to the formation of planets, gravity is the pervasive force that initiated and continues to govern the evolutionary processes of the universe. It's not just a rule of nature, but the fundamental architect behind every star and world we observe, including our own. As we embark on a journey to understand how planets form and evolve, it's crucial to first grasp gravity's pivotal role. Without its initial pull, there would be no cosmic dust merging, no stellar nurseries, and ultimately, no planets for life to inhabit. It is the initial spark and the continuous influence. The story of planet formation begins not with solid ground, but with an immense, diffuse cloud of gas and dust, known as a molecular cloud. These cosmic nurseries, light years across, are the raw material for stars and planets. Gravity, ever present, begins its work here, subtly drawing together the scattered particles. According to the widely accepted nebula hypothesis, this vast cloud of primarily hydrogen and helium, enriched with heavier elements from supernovae, starts to collapse under its own gravity. As specific regions within the cloud become denser, their gravitational pull intensifies, drawing in more and more surrounding material. This collapse isn't uniform. Slight irregularities in the cloud's density mean some regions accumulate mass faster than others. As these pockets of gas and dust grow, they also begin to rotate. This rotation is a direct consequence of the conservation of angular momentum, much like a spinning ice skater gathering speed as they pull their arms in. As the cloud spins and contracts, its initial irregular shape flattens into a vast, rotating disk, the protoplanetary disk. This disk contains the vast majority of the cloud's mass, with a dense, hot core at its center. This disk is where the true alchemy of planet formation begins. The central, most massive part of this collapsing cloud continues to gather tremendous amounts of matter. Its increasing density and pressure cause its core to heat up dramatically. This intense gravitational compression is the critical step towards igniting nuclear fusion, marking the birth of a protostar. The heat generated by the forming protostar plays a crucial role in shaping the disk. The inner regions become hotter, pushing away lighter elements like hydrogen and helium, leaving behind heavier, rocky materials. Further out, where its cooler, icy compounds can condense and remain. This temperature gradient profoundly influences what kinds of planets will form where. Within this protoplanetary disk, the dust grains, initially microscopic, begin to collide and stick together. This process, driven initially by electrostatic forces, is the first step in building larger objects. It's a slow, gentle aggregation, unlike the violent collisions of fully formed planets. As these dust grains accumulate, they form pebble-sized aggregates, then increasingly larger clumps. This growth mechanism is known as accretion. Each tiny collision, each sticky encounter, contributes to building bigger and bigger building blocks for the future planets. The forces within the disk are not just constructive. Turbulent gas motions can also break apart clumps, setting a continuous cycle of growth and destruction. However, the overall trend, driven by gravity's desire to pull things together, is towards larger formations. This initial stage of dust accumulation is critical. It bridges the gap between microscopic particles and sufficiently large objects that gravity can begin to play a more dominant role in their growth, transitioning from simple collisions to true gravitational attraction. As the accumulated clumps reach sizes of kilometers, they are no longer mere dust aggregates. They become planetesimals. These are the true seeds of planets, rocky or icy bodies large enough that their own gravity becomes the primary force governing their interactions and further growth. Within the swirling protoplanetary disk, these planetesimals orbit the young protostar, constantly colliding with one another. Unlike earlier, gentler encounters, these collisions are now driven by their increasing gravitational pull, leading to a much more efficient growth process. Most collisions between planetesimals result in destruction, shattering the objects into smaller fragments. However, a small percentage of these collisions are constructive, where the two bodies merge, adding their masses together. These successful mergers are critical for building larger planetary embryos. This runaway accretion phase is characterized by a few lucky planetesimals quickly outgrowing others. Once an object reaches a certain size, its gravitational cross-section increases dramatically, allowing it to attract and sweep up, surrounding material much more efficiently than its smaller neighbors. The largest planetesimals, those that win this gravitational race, rapidly clear out their orbital paths. They grow into massive protoplanets, becoming the dominant gravitational influences in their localized regions of the disk. These are the embryonic stages of the planets we know today. The process is not entirely orderly. The growing protoplanets also scatter smaller planetesimals through gravitational slingshots, some into the outer reaches of the system, others into highly eccentric orbits, or even out of the system entirely. This helps clear the disk, but also distributes material. The rapid growth continues until the larger protoplanets have effectively consumed or ejected most of the accessible material in their orbital zones. This phase effectively determines the final number and initial spacing of the planets in the nascent solar system. It seems dramatic. Runaway accretion is rapid on astronomical timescales, taking only hundreds of thousands to a few million years. This relatively swift sweep-up of material ensures planets can form before the gaseous disk dissipates, a crucial deadline for giant planet formation. Without gravity, this entire process would be impossible. It is the fundamental driving force that compels tiny particles to coalesce, grows planetesimals into protoplanets, and ultimately shapes the initial architectural blueprint of a young planetary system. Once protoplanets form, gravity's role transforms from building blocks to orchestrating their complex orbital dance. The gravitational interactions between these growing worlds, as well as with the central star and the remnants of the disk, are incredibly dynamic and constantly evolving. Immediately after formation, the early solar system was a chaotic place. Gravitational tugs between nascent planets, residual gas, and countless smaller planetesimals led to significant orbital instabilities and rearrangements. Planets weren't simply born into their final orbits. These gravitational interactions could drastically alter orbits, pushing planets closer to or further from the star, or changing their orbital inclinations. This planetary migration is a significant concept, explaining why we find gas giants so close to their stars in other systems. For our own solar system, the Grand Tack hypothesis suggests that Jupiter, in its early life, migrated inward towards the Sun before being pulled back out by Saturn's gravitational resonance. This massive gravitational shift would have profoundly impacted the asteroid belt and inner planets. The gravitational influence of the largest planets played a crucial role in clearing out the remaining debris from the protoplanetary disk. They acted like cosmic vacuum cleaners, absorbing some material and ejecting much of the rest into the outer reaches of the solar system. These violent gravitational encounters were not just destructive, they also shaped the distribution of smaller bodies. For instance, the gravitational stirring of the asteroid belt by Jupiter prevented the material there from coalescing into a single large planet. The resonant interactions between planetesimals and the disk's gas also played a part. Gas drag could cause objects to spiral inwards, while gravitational nudges from larger planets could create gaps or shepherd smaller bodies into specific stable regions. While chaotic, this early gravitational dance was instrumental in setting the stage for the relatively stable orbits we observe today. The major planets settled into their primary positions, having cleared most of the significant residual material from their paths. However, the settling wasn't absolute. A period of intense bombardment, known as the Late Heavy Bombardment, is hypothesized to have occurred later, where gravitational instabilities in the outer solar system potentially flung a barrage of icy and rocky bodies inwards, impacting the inner planets. These impact events, driven by gravity's ability to gather and accelerate objects, added new material to the growing planets, but also caused immense surface disruption and heat. Our moon's formation is one dramatic example of such a collision. Thus, orbital dynamics in the early solar system were not a gentle waltz, but a powerful, gravity-driven ballet of accretion, migration, and occasional cataclysm. This foundational period shaped the ultimate architecture and composition of our planetary neighborhood. Having formed from the same protoplanetary disk, the inner planets, Mercury, Venus, Earth, and Mars, are distinctly rocky, a direct consequence of the higher temperatures closer to the Sun. Gravity played a crucial role in their accretion, pulling together these denser, heavier elements. These terrestrial worlds are characterized by solid, silicatrock surfaces and metallic cores. Gravity's strength was sufficient to compact the initial rocky planetesimals into dense, cohesive bodies, distinguishing them from the more diffuse gas giants. The mass of a terrestrial planet dictates its gravitational pull, which in turn influences its ability to retain an atmosphere. Larger, more massive planets like Earth can hold onto lighter gases better than smaller worlds like Mars or Mercury, which have largely lost theirs. Gravity also influences the internal structure of terrestrial planets. The immense weight of overlying material creates extreme pressure at the core, influencing the state of matter, solid or liquid, within the planet's interior. The density and composition of the initial accretion disk, combined with the local gravitational field, determined the initial size of these rocky cores. The snow line, for instance, where volatiles could condense, influenced how much icy material could contribute to a planet's total mass. For Earth, the availability of water, brought by icy impacts from further out in the solar system, significantly contributed to its eventual form. Gravity's shaping pull not only built the planet, but also gathered the essential elements for its future oceans. Mars' smaller size and weaker gravity meant it cooled faster and couldn't retain a thick atmosphere or sustain widespread geological activity for as long as Earth, leading to its current cold, dry state. Gravity is literally the planet's life support system. Mercury, being the smallest terrestrial planet and closest to the Sun, suffered the most extreme fate. Its weak gravity couldn't hold onto any significant atmosphere, and its proximity to the Sun meant any volatiles quickly evaporated, leaving a barren, cratered wasteland. Venus, despite being similar in size to Earth and having a thick atmosphere, demonstrates gravity's hand in shaping a different outcome. Its runaway greenhouse effect, combined with its mass and proximity to the Sun, led to an extremely hot, inhospitable surface. In essence, gravity dictates the ultimate size, internal pressure, and atmospheric retention of terrestrial worlds, profoundly influencing whether they remain rocky giants or become desolate, airless bodies. It's the invisible hand behind their unique planetary personalities. Once a celestial body reaches a certain size, its gravitational field becomes strong enough to pull all its constituent materials towards its center. This immense pressure on the interior leads to a process called planetary differentiation, separating materials by density. This is why planets have distinct layers: a dense, metallic core composed primarily of iron and nickel at the center, surrounded by a less dense, rocky mantle, and finally, a lightweight outer crust. It's gravity's way of sorting materials into an organized structure. The process of differentiation is primarily driven by melting. As the planet grows through accretion, the kinetic energy of impacts, along with the decay of radioactive elements, generates significant internal heat, liquefying the planet's interior. Once molten, heavier materials like iron and nickel, under the pervasive influence of gravity, sink towards the planet's gravitational center, creating the core. Lighter silicate materials float upwards, forming the mantle and crust. This process is analogous to oil and water separating, but on a planetary scale and with immense pressure. It is gravity that provides the constant downward force, pulling the heavier components inwards. The energy released by differentiation itself, as heavy materials fall towards the center, also adds to the planet's internal heat budget, sustaining the molten state necessary for the process to continue. It's a self-reinforcing, gravitational feedback loop. Planetary differentiation is not just about layering, it's also fundamental to geological activity. The existence of a distinct core and mantle enables processes like convection and volcanism, which are essential for shaping the planet's surface and maintaining geological cycles. The size of a planetary body profoundly impacts its ability to differentiate. Smaller objects, like asteroids, do not have enough internal heat or gravitational pressure to fully melt and separate into distinct layers, remaining largely undifferentiated. Even giant planets differentiate, though their rocky cores are formed differently. For gas giants, gravity pulls their initial aggregate of rock and ice towards their center, forming a dense core, which then attracts massive envelopes of gas. In summary, planetary differentiation is gravity's masterpiece of internal organization, transforming a chaotic mix of cosmic debris into the layered, geologically active worlds we observe, setting the stage for their dynamic evolution. A differentiated planet isn't a static entity. Its interior is a dynamic inferno, driven by immense internal heat. Gravity, by compressing and holding this material, contributes significantly to this heat through initial gravitational collapse and continued pressure heating. The decay of radioactive isotopes within the mantle and core is the primary source of this ongoing internal heat. Elements like uranium, thorium, and potassium continuously release energy, warming the planet from within and countering heat loss to space. This immense internal heat drives mantle convection, a slow but powerful churning of the planet's rocky mantle. Hot, less dense material rises towards the surface, while cooler, denser material sinks back down, creating colossal circulation cells. Gravity influences convection by ensuring density differences cause movement. The sinking of cooler, denser material is directly driven by its greater gravitational pull, initiating the downward leg of the convection current. This convective motion acts like a planetary heat engine, transporting heat from the deep interior towards the surface. Without it, the planet's core would cool much faster and geological activity would cease. Evidence of this internal heat and convection is visible in phenomena like volcanism and hot springs on Earth. These are direct manifestations of the planet expelling heat from its deep interior. For gas giants, internal heat is also crucial. Residual heat from their formation and ongoing gravitational contraction generate immense internal pressures and temperatures, preventing them from simply being cold, inert balls of fluid. The heat and convection within gas giants also drive their powerful atmospheric dynamics, creating the swirling bands, storms, and immense pressures characteristic of these massive worlds. The sustained internal heat, fed by radioactive decay and gravitational energy, is a critical factor in a planet's long-term geological evolution and surface habitability. Without it, worlds would quickly become geologically dead. In essence, gravity provides the initial compression for internal heating, helps separate materials to enable convection, and then, through convection, drives processes that shape the very surface of a planet, a truly continuous sculpting force. Earth's most dynamic geological feature, plate tectonics, is a direct consequence of the planet's internal heat engine and, fundamentally, gravity. It reshapes our continents, builds mountains, and drives volcanic activity. The immense convective currents within the Earth's mantle exert drag on the overlying lithosphere, the rigid outermost layer. This drag slowly pulls apart the tectonic plates, creating diverging boundaries, or pushes them together, causing earthquakes and volcanic eruptions. Gravity plays a specific role in plate tectonics through slab pull. As a dense oceanic plate cools and becomes heavier, its increased density causes it to sink back into the mantle at subduction zones, pulling the rest of the plate along with it. Another gravity-driven mechanism is ridge push. At mid-ocean ridges, where new crust is formed, the elevation is higher due to rising magma. Gravity then causes this elevated, newly formed crust to slide downhill away from the ridge, pushing the plates apart. The combined effects of mantle drag, slab pull, and ridge push demonstrate how gravity provides the constant, sustained force necessary for plate movement, keeping Earth's surface in a perpetual state of slow but dramatic reconfiguration. Without gravity, there would be no reason for denser cooled slabs to sink, no downhill slide from ridges, and thus, no plate tectonics. The Earth would likely be a geologically inert, single-plated world like Mars or Venus. Plate tectonics is fundamental to Earth's long-term habitability. It cycles carbon from the atmosphere into rocks and back again, regulates global temperature, and creates diverse habitats. Gravity underpins this life-sustaining cycle. Even the formation of mountain ranges is a gravitational dance. When continental plates collide, the immense pressure causes the crust to crumple upwards, creating towering peaks, which are then further shaped by erosion, itself driven by gravity. The unique interplay of Earth's size, internal heat, and a liquid core allows its gravity to power plate tectonics, setting Earth apart as a dynamic, evolving planet. This delicate balance is rare in the solar system. In essence, gravity is not just the reason for Earth's layered interior, but also the engine that drives its surface dynamics, making it a continually renewing and life-supporting world. A critical factor for a planet's habitability is its ability to retain an atmosphere. Gravity is the primary force preventing atmospheric gases from escaping into the vacuum of space, holding them close to the planet's surface. The stronger a planet's gravitational pull, the greater its escape velocity. The speed an object needs to break free from its gravitational influence. For gases, this means only the fastest-moving molecules can escape. Our Moon, for example, is too small and has insufficient gravity to hold onto a significant atmosphere, which is why its surface is a desolate vacuum exposed to cosmic radiation. The temperature of a gas also matters. Hotter gas molecules move faster and are more likely to reach escape velocity. This is why planets closer to the Sun generally have thinner atmospheres unless they are very massive. Venus provides an excellent example. Despite being Earth-sized, its proximity to the Sun meant its lighter hydrogen and helium molecules escaped early, and its runaway greenhouse effect created a thick, hot atmosphere dominated by heavy carbon dioxide. Earth, with its moderate size and distance from the Sun, has the Goldilocks combination of gravitational pull and temperature to retain its life-sustaining nitrogen-oxygen atmosphere. This balance is critical for liquid water and temperate conditions. Magnetic fields, generated by a planet's liquid core, also play a key role in atmospheric retention by deflecting harmful solar wind particles that could otherwise strip away the atmosphere. Gravity enables the liquid core that produces this field. Giant planets, with their immense gravity, easily retain massive amounts of light gases like hydrogen and helium, forming their thick atmospheres and liquid metallic hydrogen layers, which differentiate under extreme pressure. Composition of primordial gas in the protoplanetary disk also played a role. Planets forming further out simply had more raw light elements available for gravity to accrete and hold onto. In essence, a planet's mass, and by extension, its gravity, along with its temperature, determine its atmospheric fate. Gravity is the fundamental guardian of a planet's breathable air, or lack thereof. Beyond simply layering, gravity plays a crucial role in shaping a planet's magnetic field, a vital shield against harmful solar radiation. This field is primarily generated by a planet's dynamo effect within its liquid core. For Earth, the outer core is a vast ocean of molten iron and nickel. Gravity's immense pressure makes it liquid, and the planet's rotation, combined with heat-driven convection currents within this liquid metal, creates a geodynamo. These swirling, electrically conductive currents in the liquid core generate powerful magnetic fields that extend far out into space. Without a liquid core, or without its motion, there would be no significant magnetic field. Mars's small size meant its core cooled and solidified much faster than Earth's. With a largely solid core, its geodynamo shut down billions of years ago, leaving it with only remnant, localized magnetic fields. This lack of a global magnetic field left Mars vulnerable to the solar wind, which gradually stripped away much of its early atmosphere and surface water, contributing to its current desert-like state. Gravity set the stage, and then gravity couldn't sustain the dynamo. Venus, despite its size similar to Earth's and likely having a molten core, exhibits a very weak magnetic field. The precise reasons are still debated, but theories suggest its slow rotation might be insufficient to drive a strong dynamo. Gas giants like Jupiter also possess incredibly powerful magnetic fields. Their liquid cores are not molten iron, but rather a vast ocean of liquid metallic hydrogen formed under immense gravitational pressure which conducts electricity. This metallic hydrogen, compressed by Jupiter's colossal gravity to extraordinary densities, behaves like a liquid metal, enabling a dynamo effect far grander than Earth's. The magnetic fields of gas giants protect them and their numerous moons from the intense solar wind, sometimes creating dazzling auroras that are far more extensive than Earth's. Ultimately, gravity is the master architect of a planet's essential life support systems. It creates the liquid core necessary for magnetic fields, which, in turn, protect the atmosphere, enabling the conditions for life to flourish. Among the most spectacular creations of gravity are the gas giants. Jupiter, Saturn, Uranus, and Neptune are colossal worlds, not of rock, but of swirling hydrogen and helium gas, compressed by their immense gravity into unique states of matter. These giants formed in the colder, outer regions of the protoplanetary disk, beyond the snow line, where abundant volatile materials like water ice, methane, and ammonia could condense, allowing for the accretion of massive ice rock cores. Their formation theories diverge, but one prominent idea is core accretion. Here, gravity helps a solid core of rock and ice grow to roughly 10 times Earth's mass through planetesimal impacts, much like terrestrial planets. Once this massive core forms, its immense gravity becomes powerful enough to rapidly pull in and accrete vast amounts of the surrounding hydrogen and helium gas directly from the protoplanetary disk. This process is incredibly efficient. This rapid gas accretion leads to the enormous sizes of gas giants, far surpassing anything rock can achieve. Gravity, by compressing this gas, creates extreme pressures that form exotic states of matter, such as liquid metallic hydrogen within Jupiter and Saturn. Another theory, disk instability, proposes that gas giants can form directly from the protoplanetary disk. Under certain conditions, a portion of the disk's gas can become gravitationally unstable and rapidly collapse, forming a giant planet without a solid core. This rapid collapse, driven entirely by the self-gravity of the gas, could form a giant planet within mere thousands of years, much faster than core accretion. This explains why some exoplanets are found with their host stars very early in their lives. The mass and composition of the nascent gas giant's atmosphere dictates its appearance and dynamics. Jupiter's vibrant bands and storms and Saturn's rings are all a result of the intricate interplay of internal heat, rotation, and gravity. Once formed, the immense gravitational pull of gas giants continues to shape the outer solar system, influencing the orbits of comets, asteroids, and even sculpting entire regions like the Kuiper Belt. Whether by core accretion or disk instability, gravity is the ultimate architect of gas giants, building worlds of immense scale and exotic composition, fundamentally different from their rocky inner siblings. Jupiter, the largest planet in our solar system, wields immense gravitational power. Its mass, more than twice that of all other planets combined, makes it the dominant gravitational force after the Sun. This colossal gravitational pull has profoundly shaped the solar system, particularly the asteroid belt between Mars and Jupiter. Jupiter acts as a gravitational shepherd, influencing the orbits of countless asteroids. Instead of allowing the material in the asteroid belt to coalesce into a planet, Jupiter's gravitational influence stirred up the region too intensely. Constant perturbations and high-speed collisions prevented stable accretion. This gravitational stirring led to the fragmentation of many aspiring planetesimals, continually breaking them into smaller pieces rather than allowing them to grow into a cohesive planetary body. Jupiter's gravity also created gaps within the asteroid belt known as Kirkwood gaps. These are regions where the orbital periods of asteroids are in resonance with Jupiter's, leading to gravitational kicks that eject objects from those specific zones. Furthermore, Jupiter captured numerous asteroids into stable, resonant orbits called Trojan points, located ahead and behind Jupiter in its own orbit around the Sun. These are gravity's stable parking spots. Without Jupiter's dominant gravitational presence, the asteroid belt would likely have formed a fifth rocky planet, or at least a much larger protoplanetary body. Its influence prevented this outcome. Jupiter also controls the behavior of many comets in the outer solar system. It can fling them inwards towards the Sun, leading to spectacular close approaches, or eject them entirely from the solar system. This massive guardian is often credited with protecting the inner solar system from excessive bombardment by either deflecting or capturing potentially hazardous comets and asteroids. It's a cosmic bodyguard. Thus, Jupiter's gravitational dominance is not merely a characteristic, but a defining feature that has fundamentally shaped the distribution of matter and the evolutionary pathways of our entire solar system. Saturn's rings are arguably the most iconic and beautiful gravitational sculptures in the solar system. This intricate system of billions of icy particles, ranging from dust grains to house-sized boulders, is held in a delicate balance by gravity. The Roche limit is a crucial gravitational concept here. If a celestial body, like a moon, approaches a massive planet too closely, the planet's tidal forces, or differential gravity, can pull the smaller body apart. For Saturn, it's believed that a small moon or several smaller bodies ventured inside Saturn's Roche limit and were tidally disrupted by its immense gravity. Their remnants then spread out to form the rings. Gravity continues to operate within the rings themselves. Collisions between individual particles, though frequent, are mostly gentle, with gravity helping to reaccrete fragmented material back together. The intricate structure of the rings, with their distinct gaps and ringlets, is sculpted by the gravitational influence of Saturn's numerous moons. Even small, shepherd moons embedded within the rings create visible gaps. These shepherd moons, though tiny compared to the rings, exert enough gravitational pull to create resonance with the ring particles, effectively clearing out specific orbital paths and creating the observed divisions. Moreover, larger, more distant moons can also affect the rings through more subtle gravitational resonances, creating spiral density waves that propagate through the ring system, adding to its complex beauty. Rings are not static. The gravitational interactions are dynamic, constantly reshaping the ring particles and causing them to migrate slowly inwards or outwards over immense periods. The existence and stability of Saturn's rings are a testament to the power of gravity working on a vast collective of small particles, creating a magnificent planetary adornment that has lasted for millions to billions of years. Without Saturn's immense gravitational field and its delicate dance with its moons, these magnificent rings would either never have formed or would have dispersed long ago, illustrating gravity's role as both creator and preserver. The gas giants, with their immense gravitational fields, are not only titans themselves, but also gravitational traps for numerous moons. These moons range from small, irregular captured asteroids to large, geologically active worlds. Some of these moons, particularly the smaller and more irregularly shaped ones, are thought to be asteroids or comets that wandered too close to a giant planet and were subsequently captured by its powerful gravitational pull. Many of these captured moons orbit in retrograde motion, meaning they orbit in the opposite direction to their planet's rotation, a telltale sign of their captured origin as opposed to having formed in the planet's original accretion disk. Even moons that formed alongside their giant planets were still heavily shaped by gravity throughout their history. The inner Galilean moons of Jupiter, for example, demonstrate a gradient of geological activity tied to their orbital distances. The closest moons experience powerful tidal forces from their massive planets. This gravitational squeezing and stretching generate immense internal heat within the moons, fueling geological activity like volcanism on Io. Europa, another of Jupiter's moons, is believed to harbor a vast subsurface ocean of liquid water, kept warm by these same tidal forces. This internal heat, driven by gravity, could make Europa a prime candidate for extraterrestrial life. Ganymede, the largest moon in the solar system, shows signs of past geological activity and even possesses its own magnetic field, indirectly a result of Jupiter's immense gravity powering its internal dynamics for a time. Tidal forces also influence the rotation of moons, often leading to them becoming tidally locked, meaning one side perpetually faces their host planet, much like our own moon faces Earth. Beyond our solar system, exomoons are also gravitationally bound to exoplanets. The search for habitable exomoons focuses on those experiencing tidal heating within the habitable zones of their parent stars. The diversity and activity of the moons of the outer system serve as a powerful testament to gravity's multifaceted influence, capturing stray bodies, powering internal heating, and sculpting their icy surfaces into unique cosmic wonders. Tidal forces, a subtle yet powerful manifestation of gravity, describe the differential gravitational pull exerted by a large body on different parts of a smaller body. It's not just the overall pull, but the asterisk difference in pull. This differential pull stretches and distorts objects, creating bulges on both the side closest to the massive body and the side furthest away. For Earth, this phenomenon is most evident in oceanic tides. While oceanic tides are familiar, similar tidal forces act on the solid Earth, causing microscopic bulges and internal friction that generate heat. This tidal heating can have profound geological consequences. Jupiter's moon Io provides the most extreme example of tidal heating. Situated incredibly close to Jupiter, Io is constantly squeezed and stretched by the gas giant's immense gravity, making it the most volcanically active body in our solar system. The gravitational interactions with Jupiter and its other large moons, Europa and Ganymede, maintain Io's slightly elliptical orbit. This dynamic ensures that the tidal forces on Io are constantly changing, generating friction and heat. Europa, further out from Jupiter than Io, experiences less intense but still significant tidal heating. This heat is thought to be sufficient to maintain a vast subsurface ocean of liquid water beneath its icy crust. Saturn's moon Enceladus is another fascinating example. Its south pole is actively spewing plumes of water ice and vapor into space, evidence of a subsurface ocean heated by tidal forces from Saturn. Tidal forces can also lead to tidal locking, where a body's rotation period matches its orbital period, always presenting the same face to its larger companion. Our moon is tidally locked to Earth. In binary star systems or exoplanetary systems, extreme tidal forces can completely reshape worlds, causing intense volcanism on super-Earths or heating rogue planets that were captured. From shaping oceanic currents to powering internal geological engines, tidal forces reveal gravity's dynamic and subtle influence, constantly stretching, heating, and molding worlds throughout the cosmos. Orbital resonances occur when the orbital periods of two or more celestial bodies are related by a simple ratio of integers. These gravitational alignments can profoundly influence planetary systems. In such resonance, The gravitational tugs between the bodies are repeated at regular, synchronized intervals, leading to cumulative effects that can either stabilize or destabilize orbits. For instance, Neptune and Pluto are in a 3-2 orbital resonance. While their orbits cross, Pluto's path is choreographed such that it never collides with Neptune, a testament to gravity's stabilizing dance. The Kirkwood gaps within the asteroid belt are defined by resonances with Jupiter. Asteroids trying to orbit in these resonant zones experience repetitive gravitational kicks from Jupiter, forcing them out. Saturn's rings are also heavily sculpted by orbital resonances with its moons. The Cassini division, a major gap in its rings, is largely due to a 2-1 resonance with the moon Mimas, clearing out particles. The Galilean moons of Jupiter, Io, Europa, and Ganymede are in a complex 1-2-4 orbital resonance. For every orbit of Ganymede, Europa completes 2 and Io completes 4. This resonance prevents the moons from settling into perfectly circular orbits. Instead, their orbits are slightly elliptical, ensuring continuous, variable tidal forces that generate internal heat, as seen in Io's volcanism. Beyond our solar system, orbital resonances are observed in exoplanetary systems, helping to explain their diverse and often tightly packed configurations. Resonances can keep multiple planets in stable, long-term orbits. While resonances can be stable, they can also trigger dramatic events. The hypothesized NICE model for our solar system's early evolution suggests a period of gravitational instability when the giant planets crossed specific resonances. This resonant crossing could have led to a violent rearrangement of the outer solar system and triggered the late heavy bombardment, demonstrating gravity's double-edged sword, stability and cataclysm. Beyond the familiar planets and their orbits lies gravity's more distant and diffuse domains. The Kuiper belt and the Oort cloud, vast reservoirs of icy bodies shaped by the Sun's weaker, but still significant, gravitational pull. The Kuiper belt is a region of icy debris extending from beyond Neptune's orbit, roughly 30 to 50 astronomical units from the Sun. It's home to dwarf planets like Pluto and Eris, and countless smaller icy bodies. The gravitational influence of Neptune significantly shapes the Kuiper belt. It shepherds many objects into resonant orbits, creating structures similar to the Kirkwood gaps in the asteroid belt. Further out, at immense distances ranging from 2,000 to 100,000 astronomical units, lies the Oort cloud. This vast, spherical shell of icy debris represents the outermost boundary of the Sun's gravitational dominance. Oort cloud objects are only loosely bound by the Sun's gravity. Their orbits are highly susceptible to gravitational perturbations from passing stars or giant molecular clouds, which can send them hurtling towards the inner solar system as long-period comets. These distant gravitational domains are cosmic fossil records, preserving primordial material largely untouched since the early days of solar system formation. They hold clues about the initial composition of the protoplanetary disk. The discovery of these distant realms confirmed gravitational predictions about where planetesimals, scattered by the giant planets, might end up. Gravity pushed them to the periphery, but still kept them connected. The objects in these outer regions are crucial for understanding planet migration. If giant planets migrated, they would have gravitationally cleared and repopulated these reservoirs of icy bodies. The mass and distribution of the Kuiper belt and Oort cloud still present mysteries, hinting at potential undiscovered planets or other gravitational influences that shaped their current configurations. From the densest cores to the most diffuse, farthest reaches, gravity defines the boundaries and contents of our solar system, maintaining a vast, interconnected web of celestial bodies, even in its most distant domains. Planet migration refers to the process where planets, especially gas giants, move from their initial formation locations to different orbits around their host star. This is a crucial, gravity-driven phenomenon. In the early solar system, protoplanetary disks contained significant amounts of gas and dust. The gravitational interaction between a forming planet and this surrounding disk material is the primary driver of migration. There are different types of migration. Type I migration involves smaller planets and is driven by torques exerted by the gas in the disk, causing the planet to lose orbital energy and spiral inwards. Type II migration occurs with more massive planets. They create a significant gap in the disk and then become locked to the viscous evolution of the disk itself, generally moving inwards with the accreting gas. Our own solar system likely experienced a period of planet migration. The Grand TAC model proposes that Jupiter initially migrated inward, then reversed direction and migrated outwards again due to a gravitational resonance with Saturn. This migration had profound consequences. It could have scattered planetesimals in the asteroid belt, preventing planet formation there, and potentially sending a barrage of icy bodies from the outer solar system towards the inner planets. The NICE model suggests an outward migration of the gas giants, pushing the Kuiper belt objects into the inner solar system, triggering the late heavy bombardment. This was a gravity-driven cosmic billiard game. Planet migration explains the existence of hot Jupiters, gas giant exoplanets found in incredibly close orbits to their stars, too close to have formed in situ, according to traditional theories. They must have migrated inwards. Understanding migration is crucial for accurately modeling planet formation and the evolution of planetary systems, as it fundamentally reshapes the initial layout dictated by accretion. In summary, planet migration is a testament to gravity's dynamic nature, not just building planets, but also moving them across vast cosmic distances, profoundly sculpting the final architecture of solar systems. Impact events, where celestial bodies collide, are a fundamental process in planetary formation and evolution. While often dramatic, they are governed by gravity, which dictates the velocities and trajectories of the colliding objects. The early solar system, impacts were the primary mechanism for accretion, as planetesimals collided and merged to form larger bodies. Gravity provided the acceleration and guided these crucial early encounters. However, not all impacts are constructive. High-velocity collisions, especially when driven by strong gravitational perturbations, can shatter objects, creating debris fields or even contributing to ring systems, as seen at Saturn. The Moon's formation is a prime example of a catastrophic impact. A Mars-sized protoplanet, nicknamed Theia, is believed to have struck early Earth, ejecting a massive amount of material that later coalesced under gravity to form the Moon. The immense energy released during such a giant impact would have largely melted both bodies, profoundly influencing Earth's initial differentiation and internal heat budget. Gravity then helped pull the debris into a new, stable body. Impact events continued long after planet formation, shaping the surfaces of most solid bodies in the solar system. The heavily cratered faces of the Moon and Mercury are stark reminders of this period of bombardment. Gravity dictates the impact velocity. A large planet's strong gravitational pull accelerates approaching objects to incredibly high speeds, leading to more energetic and destructive impacts than would occur in empty space. While destructive, impacts can also deliver essential materials. The late heavy bombardment, an intense period of impacts, possibly brought significant amounts of water and organic compounds to early Earth. Today, impacts still occur, though less frequently. Gravity continues to pull stray asteroids and comets into Earth-crossing orbits, posing an ongoing, albeit small, risk. From the constructive building of planets to the destructive sculpting of their surfaces, gravity's role in impact events is continuous and fundamental, shaping the very terrain of worlds across the cosmos. The tilt of a planet's rotational axis relative to its orbital plane, known as obliquity, profoundly influences its seasons. Gravity plays a crucial role in maintaining or changing this tilt over astronomical timescales. Earth's axial tilt of approximately 23.5 degrees is responsible for our distinct seasons. Without it, temperatures would remain relatively uniform year-round across most latitudes, lacking the vibrant seasonal changes we experience. This tilt is primarily a consequence of a giant impact believed to have formed the Moon. The immense kinetic energy of the collision likely knocked Earth onto its side, giving it its initial obliquity. Gravity, through the Moon's tidal forces, acts as a stabilizing influence on Earth's axial tilt. The Moon's gravitational tug counteracts other gravitational perturbations from the Sun and other planets that would otherwise cause Earth's tilt to vary wildly. Without the Moon, Earth's axial tilt would precess, or wobble, much more severely over millions of years, leading to extreme and unpredictable climatic shifts, potentially making the planet less hospitable for long-term life. Mars is an example of a planet with an unstable axial tilt. Lacking a large, stabilizing moon, its obliquity varies wildly over geological timescales, from almost 0 to over 60 degrees. These dramatic shifts in Mars's tilt led to profound climatic changes, influencing the distribution of its polar ice caps and potentially its past habitability. Gravity's lack of steadying hand here led to planetary chaos. Even Earth's tilt isn't perfectly stable. It undergoes a slow wobble called precession, taking about 26,000 years to complete one cycle. This changes the timing of seasons relative to our orbit, caused by gravitational torques. Other Milankovitch cycles, related to Earth's orbital eccentricity and axial precession, also influence long-term climate changes, particularly ice ages. These cycles are all driven by the gravitational interplay within our solar system. In summary, gravity is not only responsible for a planet's initial tilt, but also its subsequent stability, profoundly shaping its climate, seasonal variations, and ultimately, its capacity to sustain life. Gravitational lensing is a phenomenon predicted by Einstein's general theory of relativity, where the immense gravity of a massive object, like a galaxy or a star, bends the path of light from a more distant source. This bending of light creates distorted, magnified, or multiple images of the background object. Just like an optical lens focuses light, a gravitational field acts as a cosmic magnifying glass. While primarily used to study distant galaxies and dark matter, gravitational lensing has also become a powerful tool for discovering exoplanets, especially those that are otherwise difficult to detect. Microlensing is a specific type of gravitational lensing used for exoplanet detection. It occurs when a foreground star and its orbiting planet momentarily align with a much more distant background star. As the foreground star passes in front of the background star, its gravity magnifies the background star's light. If that foreground star has a planet, the planet's own tiny gravitational field creates an additional, brief flicker or spike in the observed brightness curve. This highly sensitive technique allows astronomers to detect exoplanets, even those as small as Earth, and those orbiting very far from their stars, or even rogue planets without a host star. Unlike other detection methods, like transits or radial velocity, microlensing doesn't rely on the planet pulling on its star or passing in front of it. It directly uses the planet's gravitational influence on light itself. Microlensing discoveries tend to be single events, as the precise alignment required is rare. However, they provide crucial statistics on the prevalence of exoplanets in different orbital configurations and masses across the galaxy. The advent of large-scale surveys observing millions of stars simultaneously has significantly increased the chances of catching these fleeting microlensing events, expanding our understanding of exoplanetary demographics. Gravitational lensing is a profound testament to the power of gravity, not just as a cosmic architect, but also as an invaluable tool for uncovering hidden worlds far beyond our reach. As astronomers explore exoplanetary systems, they uncover a bewildering diversity of worlds, many vastly different from those in our solar system. Gravity's omnipresence allows for a wide range of exotic planetary configurations. Hot Jupiters are a prime example. These gas giants, often larger than Jupiter, orbit incredibly close to their host stars, with orbital periods of just a few days. Their formation and migration are a testament to gravity's dynamic actions in young systems. Their formation is best explained by planet migration, where a gas giant forms further out in the cool protoplanetary disk, then spirals inwards due to gravitational interactions with the disk gas, eventually ending up in a dangerously close orbit. Exoplanets often exhibit highly eccentric orbits, meaning they are much more elliptical than the nearly circular orbits of planets in our solar system. This eccentricity can cause dramatic temperature swings. These eccentric orbits are often the result of gravitational interactions with other massive planets in the system, or close encounters with other stars during the system's turbulent formation. Some exoplanets are found in binary star systems, where they orbit one or both stars. The gravitational dynamics in such systems are incredibly complex, creating unusual and often unstable orbital paths for planets. Others, the hot Neptunes or super-Earths, inhabit an intermediate size class, representing a continuum of planetary masses and compositions that expand our understanding of how planets assemble under gravity. The study of exoplanetary diversity continues to test and refine our models of planet formation, showing just how adaptable and varied the gravitational accretion process can be across different stellar environments. Some systems host multiple gas giants in tight configurations that defy our simple solar system model, illustrating the diverse outcomes of gravity's influence in protoplanetary disks of varying masses and structures. The sheer variety of exoplanets confirms that gravity, while universal, manifests in uniquely complex ways depending on initial conditions, stellar composition, and the dynamic interplay within each nascent system. Tidally locked exoplanets are another fascinating consequence of extreme gravitational forces, particularly for planets orbiting very close to their host stars. For such close-in planets, the star's immense tidal forces have slowed the planet's rotation over billions of years until its rotation period matches its orbital period. One side always faces the star. This creates a perpetual day side and a perpetual night side, leading to extreme temperature differences across the planet. The day side can be scorching hot, while the night side is bitterly cold. The transition zone, or terminator, between these two extremes could hypothetically host temperate conditions, with perpetual twilight and constant high winds transferring heat from the day side. The atmosphere of tidally locked planets often has a single, massive, hot spot directly facing the star. This creates extreme winds as the hot air tries to expand and circulate to the cooler night side. Tidal locking is more likely for smaller, rocky planets orbiting M-dwarf stars, the most common type of star in our galaxy. Their habitable zones are very close to the star, making tidal locking common. Even giant planets can be tidally locked if they orbit extremely close to their high-mass host stars, leading to their rotation periods being synchronized with their orbital periods. For a planet to be habitable while tidally locked, it needs a thick enough atmosphere to redistribute heat from the day side to the night side, preventing extreme temperature differentials. The Moon is tidally locked to Earth, and it's why we always see the same lunar face. This familiar example shows how pervasive this gravitational phenomenon is in our own cosmic neighborhood. Tidally locked exoplanets underscore the profound and often extreme ways gravity shapes worlds, molding their rotation, climate, and potential for life in entirely unique and alien configurations. Rogue planets, or interstellar planets, are celestial bodies that wander through space without being gravitationally bound to any star. They are gravity's lost children, ejected from their birth systems. While difficult to detect, these planets are likely numerous, potentially outnumbering stars in our galaxy. Their existence is a stark reminder of the violent gravitational forces that shape stellar nurseries. Most rogue planets are believed to be ejected from their nascent solar systems during chaotic gravitational interactions with other, more massive planets or close encounters with other stars. For example, if two massive giant planets form, their combined gravitational pulls can accelerate a smaller, unlucky planet to such high speeds that it escapes the gravitational pull of its birth star entirely. These planets continue their journey through interstellar space, cold and dark, powered only by their own residual heat and potentially any internal geological activity. Some theories suggest that very massive rogue gas giants could potentially retain a thick atmosphere or even possess a subsurface ocean kept warm by internal radioactive decay or primordial heat. Rogue planets could also be captured by other stars. If a rogue planet passes close enough to another star, its gravity could be harnessed, bringing it into a new, albeit often eccentric, orbit. While it might seem chaotic, the mechanics of ejection and capture are precisely governed by the laws of gravity, calculating trajectories and energy transfers with incredible precision. The existence of rogue planets expands our understanding of habitability, suggesting that life could potentially arise on worlds not beholden to a star's light, drawing energy from within. Rogue planets are a powerful testament to gravity's dual nature, a force of creation that builds solar systems and a force of disruption that can cast worlds into endless cosmic exile, shaping their isolated destinies. The habitable zone, or Goldilocks zone, is a crucial concept in astrobiology. It's the region around a star where conditions are theoretically just right for liquid water to exist on a planet's surface. Gravity plays a paramount role here. It's gravity that holds the planet together, shapes its rocky core, and crucially, dictates its ability to retain an atmosphere thick enough to maintain surface temperatures suitable for liquid water. For a planet to be in the habitable zone, it must be the right distance from its star, not too hot for water to evaporate and not too cold for it to freeze solid. Gravity keeps the planet in that precise orbit. The planet's mass and gravity are critical for atmospheric retention. Too little gravity, like on Mars, and most of the water and atmosphere escape into space, even if the planet is in the habitable zone. A sufficient atmospheric blanket is essential for a stable climate, regulating temperature extremes between day and night and across seasons. Without gravity, this blanket would simply float away. Furthermore, gravity can drive plate tectonics on Earth-like planets, which is crucial for long-term climate regulation through the carbon cycle and providing a diverse range of chemical environments. The presence of a large moon held by gravity also stabilizes a planet's axial tilt, preventing dramatic climatic shifts and ensuring more consistent seasonal variation, beneficial for life's long-term evolution. Gravity influences the liquid outer core that generates a protective magnetic field, sheltering the atmosphere from harmful solar wind and cosmic radiation, another critical component for a habitable world. Searching for life begins with searching for planets in the habitable zone, but it's ultimately gravity's shaping hand that provides the internal and external conditions necessary for life to potentially emerge and thrive. The intricate interplay of a planet's mass, atmosphere, internal dynamics, and orbital stability, all underpinned by gravity, defines its ultimate capacity for life. Gravity is truly the arbiter of habitability. Planets are not static entities. They continue to evolve long after their fiery birth, undergoing subtle, gradual changes driven by the enduring influence of gravity over billions of years. One of the most significant changes is the cooling of a planet's interior. Over immense timescales, internal heat, generated from formation and radioactive decay, slowly dissipates into space. As a planet's core and mantle cool, the convection currents that drive plate tectonics slow down. This can eventually lead to a planet becoming geologically dead, with no more volcanism or earthquakes. Mars is Earth's future in this regard. Its smaller size and faster cooling led to its core solidifying, shutting down its dynamo and ceasing geological activity billions of years ago. Atmospheric escape also continues, albeit slowly. Over eons, the sun's radiation and solar wind can gradually strip away a planet's atmosphere, especially if its gravity is weak or its magnetic field fails. Tidal forces continue to evolve orbits and rotation rates. Our moon, for instance, is gradually spiraling away from Earth at a rate of a few centimeters per year due to gravitational interaction with Earth's oceans. The sun itself will eventually evolve into a red giant, expanding and engulfing the inner planets. Its gravitational field will change dramatically, causing profound shifts in the remaining outer planet orbits. After its red giant phase, the sun will shed its outer layers, forming a planetary nebula, leaving behind a dense, small white dwarf. This will dramatically weaken its gravitational hold on the remaining planets. Over trillions of years, the gravitational influence of passing stars and galactic tides will slowly perturb even the most distant planets and Oort cloud objects, eventually ejecting them into interstellar space. Thus, gravity, the force that assembled planets, also orchestrates their long, drawn-out evolution, from their dynamic youth to their eventual cooling, atmospheric loss, and ultimate ejection from their decaying stellar homes, a cosmic arc of existence.